Thank you, Bing, for a very nice introduction. That actually remind me many, good old days when I was at Chinese University Hong Kong. So I went to HKUST very often, and this is always a hot spot for me. And I think I haven't been back here probably for about 10 years. Time flies. Yeah, it's a long time, but I always enjoy and admire the research environment as well as the research outputs that my colleagues has delivered. And my talk today is on a random walk in big data. I know as Bing said is a buzzword, and I was hoping that I will know how to walk home. Actually, this is my department, and this is probably my office, and this is the chairman's office, so I have two offices somewhere, so I need to remember to go home. And so being here in IAS also remind me our IAS, so this may be just the home, so that I need to remind slightly different building. But of course, most of Princeton building doesn't look like this. This is just one of the more modern ones, right? So this is more like our library, and this is our graduate school. So this is probably more what we look like. And the main thing, as I said, I claim that I'm not talking of buzzwords because I was asked to write something of that kind. So in the celebration of the 50th anniversary of the Committee of Statistical Societies, so I was asked to write something, and I thought maybe what I should write. So I write about salient features of big data and the sparse solution to the high confidence sets. So basically trying, and then at the same time, the president of Chinese Academy of Science, that's Bai Chunli, invited me to write a paper for his new journal called National Science Review. And I thought maybe I expand the material here and extend a little bit, and then put on a more like a full-rounded random tour, my own view of big data, and I invite my colleague Han Liu to get involved with this, so that I think it'll give a more full perspective from computer science point of view too. So anyway, so if you are really interested in, and if I say something that I miss, the paper of this is on the web. So if you Google it, I think you will find the paper is on the web. Okay, so here's the outline of my talk. So the first thing, of course, we ask ourselves how important the big data, right? So then you have to talk about rise of big data and what big data can do for us. And then the next one, you may ask, what is the important features of big data, right? Only when you know the important features of big data, then you understand correctly what kind of thing we need to do to develop in the future in order to address the challenge due to big data. Then, of course, there's a lot of things already there, that people are in use. And then, of course, the natural thing you ask, are there any weaknesses? And now I'm asking you a more challenging question. Are we doing something wrong? Is our assumption verifiable? So this is probably more aggressive than just what is the weakness of current methods, right? So I think this is important because I see a lot of young faces here, like me. When I was young, not anymore, but I was thinking, hey, what should I do from time to time? And this is how I think I was educated, right? So when you want to do something, you ask how important the field is, what is the feature of the problem, what is the current method in use, what is the weakness, and then from then on, you know what is your contribution should do, right? So, and I'll offer you one of those solutions, which is sparse solution in high confidence sets. So this basically outline my talk. Coming here, I don't know who is the audience, and it's really difficult to write a transparency. So it's a mix of a couple of things. But the fortunate part is that there's a paper. So if you would like to read, it's there. So let me begin with introduction. So first of all, what is big data? Certainly everybody talk about it, and I don't think there's a unique definition or unique measurements. What is the big data? But basically, it's referred to large and complex data, and it could be structured, like a microarray data, like NCBI has 500,000 microarray data, right? So in this case, quite well structured. I mean, it's microarray is just like a big matrix, right? Or like a big image data, or unstructured data like a text, web, or videos, right? And those kind of problem arises very frequently from biological sciences like genomics, medicine, genetics, and neurosciences, right? It also arises from engineering like machine learning, computer vision, network modeling or network securities. It also arises in social sciences like business, economics, and nowadays popular buzzwords also called digital humanities. Now people even say digital governments, right? So you see everything now become digital. So you'll see why I have these kind of buzzwords. And of course, natural sciences like meteorology, earth science, astronomy, and so on. So all these kind of big data categorize many contemporary scientific and decision-making problems. So let's look at a few just simple examples, which we are very familiar. That is biological sciences. Right? So we often, like say bioinformatics. This has been done in the last decade, and we do like disease classification or trying to predict clinical outcomes using microarray or proteomic type of data. So in this case, each microarray probably give you 20,000 genes also, and you have clinical outcomes. You're trying to understand which genes are related to the outcome. And in genetics, you may try to understand the association studies between phenotype and the genotype, or between the phenotype as well as the gene expressions. Right? So this would be like EQTL type of studies. And in neuroscience, one of the important frontiers nowadays is we trying to understand and detect, let's say, activated voxels after stimuli in neurosciences, and so on. And in computer science, we know that there's a lot of problems on document and text classifications. Right? So the simplest document classification is the spam email versus non-spam email. Right? And we need to give computer some eyes, and we do like objective classification using curves and images and so on. And nowadays there's a lot of social media and internet data, as well as online learning and recommendation, surveillance videos, network securities. So all of those collecting tons of data that need to be processed and analyzed. Yeah, I know all of you feel hot. I feel the same way. I don't know. Of course, these kind of things, collecting tons of data, is not only in biological science and engineering, but also in social science like finance, economics, and business. Right? So the traditional data in finance include, let's say, stock, currencies, derivatives, commodities, high-frequency trades, macroeconomic data, but nowadays adding more to those is unstructured news and taxes, right? So you see those floating around on the internet. So all those become, we know that econ number one or finance number one, the price is determined by information up to this time point. And at this time point, we have all those kind of social media, tax, news, and so on, as well as, like say, computer confidence or computer or business sentiments that in the social media as well as in the internet. And talking about social media, social media contain a lot of information on economic health, right? So my mom lost job or something like that, or I spent 3 weeks and interviewed and the result doesn't come out so good. So all those kind of really data is embedded there. And about consumer confidence as well as consumer preference, maybe Vesla is a good car, supply and demands. So somebody even thinking that you could even do digital government, you do getting unemployment rates or getting about business sentiments just through social media, you may get similar information sets. And then, of course, in the business, we have tons of retail data, right? So those provide useful information on public health, economic health, consumer confidence, as well as their preferences, and so on. So we could certainly go into details on these kind of problems, but probably it would take a lot of time. But let me just say one simple thing. Let's say, suppose that you have just imagine that you have 2,000 stocks that you want to manage. So the minimum thing you need to know is the correlation among those 2,000 stocks. And the correlation among those 2,000 stocks, so 2,000 by 2,000 matrix has over 2 million elements. So, so certainly, I mean, to estimate those, let's say, covariance matrices, would be taking some, involve some quite challenges and so on. And similarly, if you were thinking of, let's say, modeling, let's say, the economic health, let's say in the United States, so suppose you want to predict the housing value in each neighborhood, and there are neighborhood correlations. So suppose there's 1,000 counties in the United States, then 1,000 counties, by 1,000 counties, if you just do a very simple, let's say, model called vector autoregressive model of order 1, that will involve already 1 million parameters. And of course, the things that influence the housing data is far more complex than just autoregressive of order 1. And so all these kind of problems, when you get into all of those kind of things, it could be quite complicated. And this is a very special example of spatial temporal data. And spatial temporal data has no monopoly in economics, right? So it could be in any natural science, like meteorology and earth science, and so on. So, and of course, if you're doing astronomy and astrophysics, there are, I mean, plenty of tons of data for you to analyze. So now, having said that much introduction, then at abstract level, you ask yourself, what big data can do for you? So, and I personally, and of course people, we are all understanding, we are trying to understand what is big data can do, but I summarize, basically there are two parts, right? So one part is, it holds great promises for understanding heterogeneity. And I emphasize heterogeneity is probably the #1 thing that big data is trying to do. So, and the heterogeneity can be done for our personalized medicine as well as services. And then the second thing is commonality in presence of large noises. And these kind of things is always from a very large pool of variables, factors, genes, environment, as well as their interactions. So for example, talking about heterogeneity, right? So we know chemotherapy could be very useful for somebody and could be very harmful for another group of people. And we really don't know much why. And somebody maybe better get the acupuncture treatment, somebody probably take a Western medicine. So these are really the heterogeneity that we would like to understand. And in the traditional small data, we have a problem with this. So imagine that, let's say if I just have 100, 200 cases, and you see some very special person, so what do we usually say in statistics or in data analysis? We label them outliers, right? And you'll never be able to know, is this outlier a true outlier or there's a deeper science behind them? But if I have 1 million cases, it's very different. The outlier that you see not so frequently now occur 1,000 times. And now occur 1,000 times, so you could certainly try to understand why, what caused that. So this only can happen when you have big enough data. And the commonality, the same thing, right? So if I drink, let's say, a cup of wine at midnight, does it help me in certain aspect of health or not? Right? So this kind of help, the signal is very weak in presence of very huge individual variations. And the answer can be affirmative. Long-term impact on health can only be done when we have big enough data. So this basically commonality as well as heterogeneity, we are all talking about big data. The sample size, the cases are big, right? And on the other hand, as I said, big data usually means two-dimensional. Sample size are big, but also the variable is also big, right? So the dimensionality. So instead of this we call P, in applied mathematics probably they're called D. Well, this is the same thing, just different notation, right? So now what is the impact of high dimensionality? So, and again, so what is the aim of high dimensional statistical data analysis. So there are two purposes, right? One purpose is the risk property. So for example, if I want to design an algorithm that enable me to do spam email, in this case, all it matters is the prediction power. As long as I could predict very precisely, I'm happy. The same way with financial investments. As long as I got a high return, low risk, I'm happy, right? So I don't really care exactly what is the black box behind it. However, in many other cases, like in genomic studies, in addition to understand and predict well what is the clinical outcome, we also would like to understand the molecular mechanism behind those. So in other words, we would like to understand biological behind those, or we like to understand the physics or chemistry behind what happened. So in this case, we want to, not only that, we also want to gain the insights of the relationship between the features, the variables you have, and the response for scientific purposes, as well as that hope to construct a better prediction rule. So for high-dimensional data, we basically have two things, right? So one thing is just to predict well, and the other thing is to predict well and understand the science behind the outcome that you see. So there are two aspects. And these two aspects sometimes lead to slightly different analysis and different philosophies and so on. Okay, so now let me talk a little bit on the features of big data. So we know what's big data make a difference from the traditional data, right? So if we know this, and I'm pretty sure what I'm saying here is just a part of the feature of big data, you could add in more to it, right? So first of all, data acquisition. No lab could collect 500,000 microarrays. It takes too long, and it's nearly impossible, and it's too expensive unless you are extreme rich. You have extreme rich, you can't do that. You don't have that many samples. So data acquisition, so usually the data is coming from multiple platforms. Maybe you use different microarray technology to measure different kind of microarray expressions, but there are different measurements, so it's have multiple platform, and the data are usually bias sampled because you just collecting deposit data, whatever you have. You have huge experimental variations. A technician in lab A and another technician in the East Coast, and they have very different skill sets and have different things, and usually those are like large scale measurements. So therefore, they inevitably have a lot of measurements errors associated with it. Now, having a place for you to deposit the data, right? So I deposit like NCBI data, a National Center of Biotechnology in Informatics. So there's a lot of data, 500,000 microarray there. So now the question is, how do you store the data, right? So what is the memory required? How do I do pre-processing? From time to time, you are not really asking all those 500,000 data sets yourself, but you are probably want just a part of it. So it certainly have a huge impact on data management. And from time to time, you just want to set some queries to get some idea about distributional results of the data. So you need to do these kind of things. And it has also huge impact on computing infrastructure. So how do I distribute files reliably and efficiently across the internet? How do I do computation using the existing resources in the world? So this would be another, the infrastructure change. And certainly it also have a huge impact on the philosophy of computation, computational mathematics. So for example, because of big data, we have now new paradigms on optimization as well as computing. Because in the traditional one, optimization probably is our purposes. And now in the large scale computing, you are not really thinking of finding the optimal solution, but you maybe just want to find the solution that close enough for you to move to the next stage of the analysis. So in the traditional, let's say Newton-Raphson type of second order methods, taking second derivative is impossible. 10,000 by 10,000 matrix is a big matrix. if I have a million by a million matrix, it's nearly impossible even to do anything, not to talk about inverse of the matrix. And so all of these kind of things I did write more on the paper, that I just showed you, because my collaborators know all those much better than I do. So I just outlined those. But for those people who want to know more details about its impact on computing infrastructure, you are welcome. So I basically emphasize on number one, and the next one is the data analysis. So what is the feature of big data? So certainly we will have noise accumulation issues. So all what we are talking about sparsity, you heard many things about it. So far only deal one problem, noise accumulation. That is, if I estimating many parameters, and each parameter has small errors, if I aggregate over a million parameters, the result could be quite bad. And we barely touch about spurious correlations. So for those people who just new to the field, what is the spurious correlation? So spurious correlation basically means something has no correlation but looks like correlation. Right? So a very similar thing is like this, right? So Hong Kong is a big city. So it's not so difficult to find somebody look like Bingyu, but have no biological relation with Bingyu. So this kind of thing is called, spurious correlation. And how do we deal with spurious correlation? And then a little bit more, even more abstract to that is called, I call incidental endogeneity, because I really don't have a good name to call for it. But temporary, I call incidental endogeneity. And this is like somebody, let's say, for example, Ying went to Central and bump into somebody he really know. And the reason is you bump somebody you really know is because the city is big, the dimensionality is high, so the chance of getting somebody you really know is high. So, and this could cause data analysis problems. So if I thinking a noise vector, we usually say uncorrelated with the variable you want predictors, but this can no longer hold when you are in the high dimensionals case. And then we also have measurements errors issues I talked before because of large scale data collections. So you have measurements errors. We usually using scanner to scan data. So whatever measurement you take, you cannot take in the face value of what you got. And then because you have, let's say, 1 million cases or 500,000 cases, so there's certain heterogeneity. You cannot assume the data are coming from a homogeneous population. So these are all the important impact of big data. And when we analyze big data, if you're thinking we are done, I thought we are far away from done because none of those issues has been seriously being addressed. The most thing we understood the most is the noise accumulation, and that's related to the sparsity issues that David Donahoe got the Shaw Award for. Right? So this is the only one issue we know probably relatively well. So now let's dive into those. So let me see for the new person, many people here relatively new, what is noise accumulation? So I said before, if I have estimated, if my decision depends on many parameters, each parameter is estimated with some errors, then when I put in the whole thing together, my result may be quite bad. Right? So this is the noise accumulation issues. So, so let me give you, so in the doing regression, statistical regression, so everybody know that when the number of variable big than sample size, you run regression or you're trying to inverse a matrix, it is degenerate rank matrix, so computer will give you a warning, so it's not directly applicable. So in other words, you cannot do it well. And if you, in terms of prediction error, the traditional statistics already have a prediction error that relate to the number of variable you use, not necessarily the number of variable that actually relate to the outcome. It's relate to the number of variable you use and divide by sample size. So when number of variable is big, the prediction error could be quite large. And now if you are talking about classification, so in the classification, there's no implementation issues. So in the cartoon picture I show you here, basically, I have two classes here. So for a future unknown observation in this query, you ask, is it belong to, let's say, class 1 or class 2? So one implementation you could do is just the nearest neighbor classifier. Right? So you just say, is the distance to the centroid here closer, or the distance to the centroid here closer? That you classify according to this simple rule. So even in such a case, you don't really have any implementation issues because you just calculate the distance to the centroids. However, each centroid, each coordinate is estimated based on the sample, right? Based on the red and the blue samples. So there are noise accumulation issues. They have signal aggregation issues, but also have noise accumulation issues. So you could really show that the classification error, depending on the distance between this point to between these two centroids, and then penalized by the number of features you use, square root of p. So the higher the dimension you are using, the more the distance you'll get it. Like the bigger the number you'll get on the distance. But if after certain dimensions, if you keep adding noise dimension into it, the distance will not increase, but you'll be penalized by square root of p. So probably a bit easier to illustrate is to give you an example. An example probably is always say more powerful than many words. So I just bring you to 4,500 dimensional space. So you could imagine it's just 4,500 genes. Okay, so not many, not very high dimension. And I give you 200 microarray each. So each class has 200 microarrays. And without loss of generality, I assume that the second class is the mean expression, gene expression, is at origin. So this, and then the first class, it has like a 98% at origin. So this 98% times point mass at 0, and then 2% I generate from double exponential distribution. So in other words, the centroid I'm imagining is one class is everything is always at origin. So it's all 45 dimensional coordinates. It's all zeros. And the other one has about 90, right? 4,500 times 2% is about 90, right? About 90 of those are non-zeros, and the biggest discrimination power is this one, right? So if you use these two dimensions to do classification, you may got a lot of classification powers. So if you use these two, you'll get a lot of classification. If you use maybe all of the features, you probably wouldn't get a classification power. So because once you go beyond 90 dimensions, so the rest you are adding is really just noise because there are no discrimination power between class 1 and the class 2. Okay, there's no discrimination power at all between these two classes. So in order to show this on the graph, so let's say if I take these two dimensions, okay, so I have, then I just project these two dimensions as a feature and then do principal components and then project on these two dimensional principal components so I could show you the picture. And if I use 100 dimensions, the same thing. I take the 100 best dimensions and then I project on the first two principal components. And here is the result you will see. So if I use only two features, the two most important features, you have a good classification power because you could easily separate these two classes, class 1 and class 2. And if I use 100 dimensions, you could still separate these two. And the reason is that for the first 90 dimensions, you also when you use 100 dimensions, you increase signals, but at the same time, you also you increase signal. At the same time, you also accumulate noises. So noise accumulation and the signal accumulation both actually cancel out. So you actually still have discrimination power. Now, if I go to 500 dimensions, if I use all 500 features, so as I say, only first 90 dimensions has signal. So the remaining, 400 I just added in is really just adding noise to it. So now if you look at the principal component direction, there's no discrimination power between these two. And if I use all the features, if I use all the features, all 4,500 genes to do classification, I will have no power at all to differentiate between class 1 and class 2. And this is all the reason due to what's called noise accumulation. So the accumulation power depending on, let's say, the distance in d-dimensional space, but it also divided by square root of d. So as the dimension go beyond 90, you never increase this summation, but you are always penalized by the number of features that you are using. So this is an issue of noise accumulation and all sparsity that we are talking about. So indeed, this is a sparsity, right? So only among 4,500 dimensions, only 90 or so has a different expressed genes between these two groups. So if you explore sparsity, the issue that I just talked here can be resolved nicely. You will have a very high discrimination power, and you will never use 4,500 dimensions. You may use 10 or 15 dimensions to do classification. And the next issue we were talking is the spurious correlation. So again, let me remind what is the spurious correlation again. Spurious correlation basically saying that two persons looks alike, but they have no genetic relation, right? So this doesn't happen in low dimensional space. This doesn't happen in small village. This only happens in a big city like Hong Kong. So in order to illustrate that, so I give you the following simple experiment, right? So I just generate a sample of size 50. So I generate 50 independent samples. And each of those random variables are independently generated from standard normal distribution. So in theory, the sample correlation between the first variable z1 and the second variable z2 should be very small. And in low dimensional case, that should be. But now in the high dimensional case, if I ask myself, what is the correlation between z1 and zj, so what is the maximum correlation? If you give me a random variable called z1, the first one you fix a direction in the n-dimensional sphere. And you are asking among the other p random variable you insert on that sphere, it's really a random packing, issues. You ask what is the maximum, what is the minimum angle you will get, right? So what is the maximum correlation you will get? So for just as small as p equal to 1,000, so if I have one, in other words, if I pack in 1,000 uniformly distributed vectors into 50-dimensional space, so the correlation you get is about this, maybe about 0.5. So in other words, so for any independent random variable z1 you give me, I can always find another random variable that have correlation about maybe 0.5, or I mean, you could calculate the cosine angle of that too. So this kind of issue is really related to, random geometric graph. So in one of the late paper we wrote for the Journal of Machine Learning, so we're asking the following very simple question. Right? So you have let's say n-dimensional sphere, and you put p data points there, and you are asking what is the minimum angle that you could pack into the data, and so you could compute that analytically. You could also asking among, let's say, p choose two different angles, what is the law of the distribution? So all those kind of things have something to do with what I'm going to say later on. But this is all related to, probability theory that's actually quite interesting in high-dimensional case. So if I do this kind of experiment, not only one time, but I do, let's say, 1,000 times. That is, I simulate a sample of size 50 of 1,000 independent random variables. So this kind of experiment I did here just once. I could do this 1,000 times. So if I do 1,000 times, I will get a distribution of the maximum correlation that you are computing here. So this is the distribution when p is equal to 1,000. And when p equal to 10,000, the dimension, that is the spurious correlation increases when you go to, let's say, if you talk about 10,000 random variables, like the microarray or the microarray gene expression data. So then the correlation increase from 0.45 probably to 0.55. That's the correlation. Now this is probably not very serious because you say, hey, p is, I mean, after all, it's 0.5. It's high, but not too high. Now, if I ask you a slightly different question, if I ask you, if you give me a Z1, which is, again, it's independent normally random variable, and I say, let me find a set of 5 genes, a set of 5 independent random variables, whose linear combination would be best predict this Z1. So this is a spurious correlation too, right? So it's a spurious correlation between Z1 and another group of 5 genes. And if you compute that, the correlation is much higher, so it's about 0.9. So if the correlation is about 0.9, then it could lead to false scientific discoveries, right? So for example, if Z1 is independent for certain kind of cancer, then you could also discover 5 genes that also have the same explanatory power to the outcome you see, because Z1 and the other 5 genes have 0.9 correlations. And adding to the words, those 5 genes could be completely independent outcomes. So we could get completely false scientific discoveries. The same thing also happened. It's not necessary to say it's the sparsest things preferred, right? So suppose 5 genes happen to be related to the one cancer. You could also find one random variable have the same explanatory power. So this could lead to false scientific discoveries. So I'm not going to explain the graph below carefully, but this is the experiment, the favorite experiment I always like my high school students to do when they do intern at Princeton. So I give them clinical outcomes, 0 and 1, let's say have some kind of event, have some kind of disease, and some kind without disease. And I also artificially generate let's say, X variables, independent normal, just tell them this is my gene expression, and ask students trying to find which genes associate with clinical outcomes. They always come up with 10 variables and so on. So this is standard spurious correlation because I know clinical outcome is the true clinical outcome, but my microarray is a random number that I give them. Right? So this is just further strengthening the concept of spurious correlation. And the spurious correlation could cause a lot of false statistical inference, which in turn feedback into the false scientific discovery too. So let me give you a very simple example for you to imagine here. So suppose that unknown to us, the data generating process is governed by this simple random law like this, and we do know that, so we really collecting a lot of data, a lot of variables, let's say 1,000 or 10,000, and now we do and then we now do variable selections. So if you do, let's say, only 2 variables, if you select correctly, the first variable must be x1, right? The second variable will be x2. So these 2 important genes that relate to the outcome, so you find it. Now if you find the third random variable, what that third random variable would be, or maybe and that third random variable would be selected to predict your realized noise, epsilon. So if I have 1,000 cases, 1,000 sample, then I have a vector of 1,000 epsilons. That's what we call noise. And if you choose one extra variable, that extra variable will be chosen to predict this epsilon. And the more you choose, the more this epsilon, the realized noise, will be predicted. So therefore, the residual variance would be, the noise level will be significantly underestimated. And once the noise level is significantly underestimated, many statistical inference could be completely wrong. You will call many genes are significant difference expressed. And when we do using a variable selection methods, lasso, scat, the stepwise addition or deletion, once you recruit a little bit, overestimate your parameter number of variables, this epsilon would be predicted very well, and you could do things very badly. So to show you just one simple example, I again do the random, do a simulation experiments. So in this case, again, I just take 1,000, very humble, 1,000 genes. So really, in the real world, we could get 10,000, could be 50,000, or much bigger variables, and the n equal to 50. And I'm trying using what's so-called stepwise addition algorithm. It doesn't matter. You could use Lasso, whichever method you like to use. Doesn't matter. So what I'm doing here is, if I overshooting, I mean, in this case, I just really the model is the same like this, but instead of taking 2 and the 0.3 here, I take those both to be 0, just easier. The same thing. Just so in other words, my true model is really is the noise itself. Whatever you select is to predict the noise. So this, if you overshooting by one variable, this is spirit correlation I showed you a moment ago, about 0.45. If you choose 2 extra variables, your spirit correlation become 0.6 something, and if you choose 10, the spirit correlation become 0.99 or something like that. And as a result, because your noise being predicted, so you will be seriously underestimate the noise level. So for example, if you overtaking 10 variables, the noise level would be truly it should be 1, but you'll be estimated about 1/10 as large. And if you do, let's say, if you overtaking chosen, let's say, 5 variables, then the noise is probably about 1/3 as large as originals. So therefore, because noise is seriously underestimated, many statistical inference can be completely wrong. If you know the issue, all I'm showing here, not going to show you how I correct it. There's a way to do it. So if you know the issue, you can always design the methods to estimate more or less correctly the right noise. So I basically trying to say is you need to know the issue first before, so that you could design a new method to address those kind of issues. And here is a third issue I want to talk, and probably I don't want to talk too many. This is probably the last issue I want to talk. And this issue raised the question, are we doing science correctly here? I know this sounds a little bit awful, so here is the typical analysis. So you'll understand what I'm saying here. Okay, here's the typical analysis. So this is, let's say, unknown to us. So we always this is the so this is idealized statistical model, right? So I'm using this simplified model to illustrate the point, and this is the same model used in applied math and so on. So so the outcome depending on, let's say, expression of genes, and then some parameters, right? It's a linear combination of those, and we assume. And this is, if you don't believe it, open any book, any paper, except probably one of my paper. Every paper make this assumption that the noise, epsilon, and your predictor x is equal to 0. And some other paper, maybe you are making a little bit stronger assumption than that. And we always assume that the support, like, is a sparse inference. So there are only a few 25 genes or 30 genes that are responsible for outcomes. So we have unknown set, which is the support of this beta 0. This is a small set. And what we really wish to find is our model selection is wish to find this small set of genes for understanding the molecular mechanism, and we also would like to estimate how important each gene's influence on the outcome, clinical outcomes. Right, so here I use in gene, but you don't have to use in gene. You could do economic studies, right? So I now change the gear. Say, hey, you go out to collect the data. Collect data. It doesn't have to be the clinical outcome. It could be unemployment rates. So you collect in each region of the United States and so on, and then you apply some kind of existing methods. So if you're in the West Coast like Lasso, right? So they're cowboys. And in the East Coast, when we are raising fish, we use scat. Whatever you do, so you'll find set as 0 and beta 0, and then you are done. Right? So you get done. Now you go home and then think about it. You start to worry are we doing the right science? So first thing you are asking, is the noise residual you get, right? And those variables are uncorrelated. I mean, you say, why I'm asking this? Because this is the line number one you assume here, right? You assume that the noise and the variables are independent. So this is line number one you assume there. So you should be based on verifiable assumptions. Now, if you think about this is a lot of assumption. If I have 10,000 genes, this is 10,000 equations there. I have to check this for 10,000 equations. 10,000, are the correlations small? Now, the next question you may ask, what is the consequence if it is not? Right? So, in other words, if there are many guys that not uncorrelated, so do I do the right science? Do I do the right statistics? And the third question, of course, is how can we do it right? So if you answer those three questions, if you know this is a problem, maybe not verifiable, then this is the question you will naturally ask, right? So I mean, which currently we never ask this kind of questions. After you do analysis, you do lasso, you do scat, and then you just walk away. I mean, you never verify the number one, the first line you make assumption that the noise and X are uncorrelated. And this has a lot of interest in the relative probability theory, you'll see. And then I could tell you what is the consequences. I could prove that the necessary condition for this guy to select the right set is this condition holds. So in other words, if this condition doesn't hold, you don't select a consistent set. Now, how do we do it right? So I'll say a few words. So again, the evidence probably say, I mean, a picture probably say more than 1,000 words, right? So the best way to show you this is to show you an example. Or maybe I show you two examples. And I believe this example could be repeated as many times as you like. And for those people who are younger people who are truly doing science, go back and try it and see what you see, right? So here I'm don't really picking anything of my favorite, just being a mathematician, asking students to get in some data and try it, right? So in this case, we have 90 microarrays from the International HAPMAP project. And in those microarrays, I have a lot of gene expressions. So we take one particular gene expression. This is called CHRNA6. Probably doesn't matter to us here. That's one of genes whose expression have something in relation to nicotine addictiveness. And then the remaining probes, or if you thinking a bit abstract, thinking this as a gene expressions. So I'm using the remaining as my X. So in other words, one gene expression as my Y, the remaining gene expression as my X. Now I calculate the correlation between Y and each of X, right? So I have 47,000 of X, so therefore I have 47,000 correlations between Y and X. And I'm plotting here as a baseline, right? So this is this is the distribution of the correlation between Y, which is the gene expression of this gene, and of the remaining. So I plot here. Okay. So now the next thing is I feed the data into lasso package. So lasso select 23 variables. And so that means 23 genes, we usually claim those are relevant to the nicotine addictiveness. And then I got the residuals. So I verify my residual, right? So for each residuals and each variable, I compute the correlation between these two. So I have 47,000 of those, and I plot is here. So now the question is, if this one looks like if epsilon is uncorrelated with them, if this one looks like a 0 to you, or it's not look quite like a 0, right? So I mean, this is the baseline. Without using any X, the correlation looks like this. After I do lasso, I take 23 the dependent of those 23 genes, and I plot it here, and this is the thing that you now see, I mean, of course, if you want to say whether this is coming from something that has zero correlation or not, you really need to know the null distribution. And if you wanted to know null distribution, this is again has something I will show you a bit more expressly related to random geometric graph. And I mean, my conclusion is more than likely most of those are not zero. And the reason is that I'll argue with a little bit more mathematically or more. Well, the reason is incidental endogeneity. That is, I have one epsilon variables, and I have so many other gene expressions. Just like by chance alone, many of those would be correlated with this epsilon. So this is the issue. So in other words, the assumption here probably not verifiable. So this is actually the next what I'm going to say is are our assumptions verifiable, right? So this is the number one in any sparse recovery assumptions. We make the assumption that epsilon and x are uncorrelated in this linear model. Now the picture I just showed you here is this is the correlation between epsilon and x, and can I conclude this is equal to 0? Or if it's not equal to 0, then I know it will give you a model selection inconsistency. And this is really the reason behind those kind of incidental endogeneity. Okay, so because we are collecting many predictors related to the clinical outcomes, and by chance alone, some of the collected predictors are actually correlate with this epsilon. So let me give you just a toy example, just as a kind of mathematical imagination to this kind of scenario. Suppose unknown to us, the true data generating process looks like this. So that is the two genes, the first two genes are related to the clinical outcome or biological outcome. And it's followed our usual friend, the correlation between x1 and epsilon equal to 0, correlation between x2 and epsilon are equal to 0. Now, of course, I don't know which two genes are, or how many genes are correlated with the outcome. So therefore, I collect a lot, right? I collect a lot of those genes, let's say the 3, 4, 5, all the way to 20,000. So I collect a lot of genes. Now I'm asking, can the assumption like this equal to 0 always hold? And the more you have, the more equation you are asking. Right? So by the way, this is just equal to epsilon from this model. Right? So in other words, is correlation between xj and epsilon are equal to 0. So the more gene you are collecting, the more likely some of those rules will be break out. Now, the original model was good. There's nothing wrong with this model. This classical statistical model looks nice. But after you are collecting so many genes in order to hope to cover this first one and other genes, you may make a lot of mistakes, right? And this is the point I want to raise is that high dimensionality actually causes incidental endogeneity. Just like big city like Hong Kong make me a lot of chance to bump somebody I know in Central. So this is due to high dimensionality. And now more mathematical definition of endogeneity, of course, means that there at least exists one variables that is correlated with the epsilon, right? So, but we could exist a lot of those variables. And I think the assumption we all assume that noise and so many other gene expressions, because noise is not really noise, it's just equal to this, right? So it's really a fiction, a mathematical fiction or statistical fiction, and it's very hard to validate. So this is really the key point I'm trying to say is that high dimensionality is a source of this kind of endogeneity, incidental endogeneity. So this is the typical scenario that what I'm imagining, right? So why is your clinical outcome, could be biological outcome, could be health outcome, could be credit risk outcome, credit outcome, or whatever it is. And we thinking that there's a group of genes that are acting together that getting biological or clinical outcomes or getting the credit outcomes. And this group of genes is unknown to you. And because it's unknown to you, you collect many of those, a very large data, unknown factor, you're putting all those together. I mean, you collect, these could be gene expression, could be macroeconomic risk and all other factors that you are putting in together. So it's very difficult because you collect a lot of those variables beyond the system as 0 that you have here, which maybe would be 20, right? You collect tens of thousands of those, and you ask this to be equal to 0, epsilon x equal to 0. That's nearly impossible, right? Not equal to 0 probably is more often. Equal to 0 probably is more rare. So now then this leads to the natural issue. Can you do some statistical inference without this kind of assumption? You say, well, yeah, somebody like David Donahoe, right? So getting Shaw Award made this assumption. Now the question is, somebody without making getting Shaw Award can also find this as 0 without making this assumption, right? So this is actually the question. As I said, this assumption is a fiction. It could be, and more than likely, cannot be held. So, I'll show you another example. So it's really the more like a rule than exception, because you are asking something nearly impossible, right? So this is the assumption that we make. Okay, like our classical linear model, right? So this is noise. So I basically say noise, X and this group are uncorrelated. I may be acting a little bit stronger. So here stronger and weaker depending on what. This is a bit stronger. If under this kind of assumption, I could uncover this group of genes that are important to the outcome, or group of variables that are important to the outcome. Or I could make it weaker, as long as epsilon are uncorrelated with those important variables, and epsilon and, let's say, x squared, right? So if I just square each of those components, are also uncorrelated. So square here is just one example, doesn't have to be square. So in other words, as long as there are two, let's say suppose there are 20, unknown to us, there are 20 genes, S0 has 20 elements there, right? So 20 variables that are responsible for the outcome. So as long as those 20 variables are uncorrelated with epsilon, and those square 20 variables are also uncorrelated with epsilon, then actually we are able to identify this set as 0, as well as making the verifiable, verifiable scientific assumptions. So let me using this example again, the example of this gene expression again. Using this data again. So based on this assumption, plus, let's say, some methods, I don't tell you, just at this moment thinking it as a black box. So we using this, we find five genes, and I also could compute the residuals. Right? So you could also get 5 genes, you could compute those residuals, and now you could verify if residuals are uncorrelated with those 47,000 different genes. If you look at that picture, you'll see that it's not. At the beginning, I worried. I said, hey, after I do so many work and efforts and prove theorems, and I show the same thing, right? That is, my epsilon cannot be, my residual is still correlated with those 4,700 variables. And this is not really something to worry about. This should be true, because but the lucky part is I never make assumption. I never make assumption that my noise is uncorrelated with the rest of variables. I only make assumption my noise is uncorrelated with your selected variables and with the square of your selected variables. Right? So I only make assumption of 10 equations rather than 4,700 equations. So this is not verifiable, is not really an issue to us, because I have never made it. So all I really need to validate is to validate those 10 equations. And if you look at it, actually I did validate here. So here is the correlation, right? So there are 5 correlations here. So these are more or less 0, right? And then square of this is not quite 0, but quite small. So this is really, so these 10 assumptions is more or less verifiable. So in other words, we do statistical analysis. We select the genes based on verifiable assumption rather than unverifiable assumptions. And I said a moment ago that these kind of issues, that is the assumption of epsilon and x are uncorrelated. So this is tens of thousands of equations that is not verifiable. If you take another data set, you verify it, you'll see that you're using Lasso or using SCAD, whatever you like, or whatever selector that you favor, and you're trying to verify this, you'll see it's not 0. And then, so here I'm just doing another data set for you so that you at least be probably a bit more convinced. So this is 148 microarrays from the geo data. And this geo data is, is again from NCBI data sets. So we take one of those genes, and this gene is related to prostate cancer as my Y. And then the remaining genes is like about 13,000 genes, right? So as my X. So again, I'm plotting here is the correlation between X and Y, and correlation between X and Y, it looks like this without doing any regression. Without doing any regression. So this is correlation between X and Y I plotted here. So now I also do lasso, and lasso give me, I forget how many, sorry, I forget to plot here, maybe about 20 genes or something like 22 or 20 or 30 genes, I forget. So I plot the residual of lassos in the red here, right? So the red distribution there. So this is the distribution. If I do in lasso, I taking out, and now this is the red picture here. So now I'm asked my question: is the red picture that that's coming from a distribution that the true correlation between X and the epsilon are all equal to 0. So in other words, the red picture you see here is just by chance, or is really there real difference here? So we do some kind of permutation just to get a null distribution. So this is the null distribution. We believe that if X and epsilon are really uncorrelated, you get a histogram like a blue what I got here. So apparently there are a lot of portion of correlation that is not 0. So therefore, again, I will conclude that the assumption that you make this equal to 0 for all xj's is not verifiable. So this is just a few issues to talking about the assumption that we make so far is not verifiable. But these also, raise a lot of interesting statistical or probabilistic kind of questions, right? The first question I ask is, how do I test incidental endogeneity? That is, if the assumption like this truly hold, okay, and my X are correlated, so epsilon and X are really independent or uncorrelated, and I have a lot of, colored rather than if it's not colored, if it's independent X, then it's a bit easier. If I have a lot of colored, the X are have some kind of correlated distributions. So and then if I do the plot like what I'm plotting here, I'm doing the plot like what I'm plotting here, calculating this. What is the distribution of the sample correlation between X and epsilon? So this is the first question and this. So in other words, what is the null distribution when X is really uncorrelated with epsilon? So this is really related to random geometric graph issues that for correlated X rather than for independent X. And then the next issue you may ask yourself, how do we do it right? So as I said, we could do analysis based on these kind of assumptions, and this assumption probably is much easier to be verifiable, but our method is very unstable to compute. So there's a lot of issues you could improve. That is, can I make much less assumption can I make much less assumption but able to find the gene that's relevant to your scientific outcome? So this is really the features of high dimensional data. So now the last thing that I want to talk is probably just a quick drive-by, just to help us understand, where the sparsity come from. We all know that when I learn, when I learn the model selection, taking step 101, so what we do really is based on what's so-called penalized archaic type of information criteria. And these are criteria based on mathematics or statistical derivation of risk estimations. And now we do lasso. Again, lasso is similarly just based, L1 penalty is really based on mathematical intuition. Really, there's no, no statistical insight. So I'm trying to provide some statistical insight. If we agree, by the way, this is only solved one issue, right? This is only solved noise accumulation issues. So it's still on sparse inference. So let me say a few quick words, then we'll wrap it up. So suppose I have data. I have x and y, so I have data, and we want to find the sparsest prediction rule to predict the loss. So I use the linear combination of x, y to predict y, and this is the expected loss, right? So this framework actually encompasses a lot of statistical studies like generalized linear models, supported vector machines, ADA boosting algorithms, or robust regression, quantile regression. So all in the same framework. You have a pair of data, you want to find best linear combination to predict y under certain kind of convex loss. So this is the issue that we are talking about. And so because I have data, so you have empirical loss, looks like that, right? So based on your data. And because your beta 0, the true parameter you want to find is solving this equation. So the derivative of the gradient of this should be equal to 0, right? So the gradient equal to 0, you could think of this as estimation equations, okay? So this is really estimation equations. Now if I ask myself, based on the data, n data, n could be big, could be medium, moderate, could be small, based on the n data point you have. So what is the data information you have? So the data information you have, you may naturally say, hey, since this is equal to 0, and I'm going to replace this by empirical derivatives, right? So empirical estimation equations. Then the confidence sets would be, say, hey, let me relax this equal to 0, relax this by a certain amount. And the norm here, I use L infinity norm because this is the norm I know that will make my set Cn convex. Other norms, I don't know whether it will be convex or not. I haven't at least studied quite carefully on that. And then because it's high dimensional, so there are so many uncertainties. So I want my confidence interval to be high confidence sets, meaning that the true beta 0 in my set has a very high probability, right? The probability will go to 1. So in other words, with probability nearly 100%, my unknown vector, unknown parameters is in my set Cn. So I call this set is the high confidence sets because the confidence interval will go to very large, go to 1. And this is really summarize all data information. Right? So based on data, that's the high confidence sets is all you have. But however, if P is very large, let's say 20,000 or 1,000,000 dimensions, so this convex set is too large to be useful. So therefore, since we are seeking for a sparse solution to minimize the errors, because we have prior knowledge, that the true vector is sparse. So a natural way to do it is say, hey, let me among my high confidence sets, right? So this is my high confidence sets. Let me find one to have the smallest, the sparsest solution, right? So let me have the smallest L1 norm. So this would be a very natural solution. That is, you trying to among high confidence sets, you're trying to find the sparsest solution. So this is in general a convex optimization problem. And this is very flexible to choose because, first of all, estimation equation I use here, you have a lot of choices you can make. And the sparsity, you could also have a lot of choices to measure this, the sparsity. So and in this way, actually, I separate very well the data information and the mathematical assumption. Right? So the data information is summarized by this high confidence sets with probably going to 1 that my true parameter is in this p-dimensional convex set. And then among these p-dimensional high confidence sets, I want a sparse solution. So this is your assumption. And this is not something unfamiliar to you. Right? So I give you an example. Denzek selector is one of these examples. Right? So if I take the least squares, and then the high confidence sets would naturally become like this. So this would be the least square solution. And now you're trying to find the sparse solution in your high confidence sets. And this is exactly what Kandel and Tao does in 2007 when I was the editor of the journal. So this is exactly what they did. And this could be easily generalized to any other loss. And the method can apply here to Gaussian graph models and high dimensional classifications. I could do all of these things. I mean, at the end of the day, I don't want to talk into the details, and you could get a very general theorems that the method you are doing here does the right thing. So, so in order not to get you bored, so let me just quickly conclude what I have talked so far. So as quick summary. So big data hold great promises for discovery of heterogeneity, as well as this, the search for personalized treatments like medicine or customer services. So they allow us to find weak patterns in presence of large individual variations, like, for example, public health issues. And the salient features of big data include, let's say, experimental variations, computational cost, heterogeneity. So in other words, IID model assumption should be removed into like a mixture of many unknown small components. Noise accumulations, spurious correlations, incidental endogeneity, as well as measurements errors, the presence of measurements errors. And I offer you a very general solution for sparsity problem. Basically, the sparse solution in high confidence sets is a good and generic solution with many flexibilities. It naturally separates the data information you have as well as the sparsity assumption you have. So it has very good statistical intuition. Where is your assumption? Where is the data information? So that we don't mix two together. And this actually applies to measurements errors, to endogeneity. It's all applied. It's just different issues will give you a different sparse confidence sets. So that's all I want to say. Thank you. Any questions?
I'm a long way removed from this stuff, so my question might be not very intelligent. Is there any connection, or do you see any connection between? So here you're saying as the dimensionality grows, you're getting these kind of effects that you wouldn't expect, right? Do you see any sort of connection between this concept and, let's say, microstructure noise, where you're basically getting something you don't expect, and it's a sort of a regression type effect. And if so, do you think you could go backwards and maybe apply some of these kind of techniques you're talking about here to that problem?
Yeah. So I don't know what you refer to microstructural noise here, but certainly that we know when you do big data, so there's a lot of measurements errors in the problems, and all those measurement error could also accumulate because you have tens of thousands of those. And the best solution is not necessary to individually remove all those kind of noises out. It's a very different challenging issues, but you may be able to design some kind of more noise resistance rule so that it doesn't have a noise accumulation issues. So the measurement error is inherent in those problems.
So in your recent paper with Liao about weakening the correlation assumption of epsilon with all the x to be only the non-correlations of epsilon with only the X state that you are interested in, the beta, the X cell, I think, using your notation, right? So, this seems to be very reasonable. On the other hand, seems to be. I mean, if one wants to only verify this assumption, then one has more tendency to select a sparse predictor. I mean, if you only select one predictor, then this assumption always holds.
Okay, so why you think one assumption is always
If
holds?
there's only one predictor, then we are only talking about the residual is always orthogonal to the one predictor. So in this case, the empirical correlation is always there.
Yeah, but I have so I think what you say is correct in the following sense. Okay, first, if I have only this equation is not adequate, I think that's probably what you are referring to. So if I have only one predictor, I have a second equation here. I ask this to hold. So I have two equations. So and I don't know whether this epsilon has to be always uncorrelated with this squared. I mean, why do you think? I still have two equations, right? And if this assumption hold, even let's say suppose this assumption hold, it doesn't mean your model is correct, right? So it's just at least I'm just saying that I produce an assumption that is internally consistent, not like lasso or sparse recovery. We produce a method we cannot be internally consistent. So in other words, you cannot verify assumption this equal to 0.
So I guess my question is more about well, if we want to verify this kind of conditions, then we will have more tendency to select more sparse predictors. So maybe we are emphasizing sparsity too much. I mean.
Oh, okay. So that's an interesting question. I cannot answer you exactly, saying I must select more sparse or I can select less sparse because I have no reference. But basically, you basically saying that the more sparse, the easier this equation to be verified. That is true. That part is true. But I do not know that if you apply our algorithm to select, at the end of the day, you are always select. For example, we select 5 genes, right? We do not select only 2 genes, right? For example. So that means it's not selecting the lowest number, but there is an issue. Remember, this is version 001, you're not version 1, right? So the first time we're trying to do it, and somebody like you, if you join the team, will maybe getting a better solution. We're just trying to find the issues. Once we know issues, then with the community at large, we'll find the solution to the problem. Like, but it's just no, the version 101, the paper you haven't been accepted by anybody, right?
Any more questions? Can I take a look at that confidence set,
Okay.
slide?
This?
Yeah. I think you have another one that says density selector,
Right.
satisfy that condition.
Yeah.
On one occasion, I heard someone working in this density selector at Lasso. She told me that they are cousins. They're closely related.
Right.
There are many properties that are similar. So my question would be, Lasso does it satisfy this?
Well, Lasso is okay. Lasso and density, you are right. So they are very close in properties. They are equal in many ways. So does Lasso exactly satisfy this? If you using large enough space, so creating loss function like what we're creating here, you could possibly or approximately the same, and the solution approximately solution to this sparse high confidence sets region. So in other words, lasso may not necessarily exact solution to this, but it will be an approximate solution to this
So
problem.
maybe there's similar result.
Right.
Not exact same result will hold.
Right. Yeah, so I mean, the main reason I'm talking about this is using this just to motivate a general solution with which separate data information and assumption. Remember, when we do penalized least squares, we don't know which one is your assumption, which is the data, right? So here now I separate quite well, right? So this high confidence region is your data, all your data information. Minimizing this spaces is your assumption because you prefer among so many indifferentiable solutions, you prefer the sparser solution. So we differentiate the assumption from the data. But this is a good question.
What is the computational complexity of your solution?
This issue, right?
Yes.
Okay, very good one. So this one is a convex optimization, that's for sure. It's a convex problem. And I just wrote in the summer, just as a rule, just to a general solution to the sparse problem. So they provide a kind of understanding why we get a solution like that. So I never devise any solution to this kind of complex problem. But I assume Danzig selected in the problem I'm writing here is a linear programming problem. And for the let's say classification I wrote there is a quadratic programming problem. So usually we try to, for special cases, if it's not a general loss, it could be a linear program or quadratic programming problems. But for more general loss is a convex optimization subject to the linear constraints type of things like that.
Well, you have several problems with high dimensional data.
Mm-hmm.
One is computational complexity.
Right.
One is the lossless accumulation.
Mm-hmm.
So if this is not efficient enough, basically you're offering a solution to one problem
Mm-hmm.
which suffers from another problem.
Yeah, no.
And you actually don't have a solution.
No, this one would not have any more expensive computation than penalized least squares issues or penalized likelihood issues. It's the same complexity. I'm offered this solution is enable you to find a general understanding why our solution looks like that, a more unified solution to this kind of problem, and enable you even to get a general theorem about what is the risk properties. So this is that's all I'm talking. So now the computation issues, I am one person. I can't solve all those problems. But I mean the main reason I write in this way is to make sure is a convex optimization problem, so that somebody like you may be able to develop the algorithm. I think the issue of big data, it should be coordinated. I mean, at the beginning, you see at my summary, between computer science, computational math, and statistics. Because if we define procedure wrong, we will ignore all those kind of endogenous measurements error, heterogeneity wrong. The thing you are minimizing at the end of the day maybe is the wrong target. And if you know how to minimize, but enable to distribute data properly to different places, we also have problems. This really should be a coordinating a big community efforts. So I talk about statistic issues here is the area that I know the best. But I know that it should be a broad collection among bigger scientific community rather than a few people themselves.
My question is also related with that verifiable assumption.
Mm-hmm.
Now, I understand this may be the first crack on a very hard and important problem, but suppose you, because you don't assume anything on the dependence of the error on outside the covariance in your S0, then what happens if it happens that there is an xj outside your S0, but it's exactly your error?
Can you say that again?
Problem?
Can you say that again?
I mean, what if there are some other variable which is very strongly related with the regression error? Would that be a problem if that variable is not in your S0?
Yeah, that would cause a lot of problems. Right? So that's a problem I'm trying to avoid. So that is, I trying to make assumptions that, okay, so the basic philosophy is this. This has a lot of equations. Even though I write it into one, there will be tens of thousands of equations. And more than likely, tens of thousands of equations hold is nearly impossible. So we're trying to reduce the assumption as less as you can. And so the reduction that we can make so far is an assumption like that. So which is have maybe, if it's sparse, it's twice as your sparse equation. Let's say if there are 20, it will be 40. If there are 5, it will be 10 equations. So now the assumption outside these sets, I don't ask. I don't ask whether it's 0 or not 0, whether it's strong or weak. It's no matter to me because as long as with this assumption, I'll be able to find this set as 0.
You mean no matter how strong the other variables depend on the error, that's not going to affect your eventual?
I think if under these assumptions, it will not be as much affect our model selection consistency. That's actually the result that we analyzed. But
thank you.
Thank you.
Okay, I guess we have to wrap up. Okay, let's thank Professor for.
Okay, thank you all for attention. Thank you.